So how do we get the other logs? We use this identity, or a nice algebraic identity, that if I look at the natural log of u, um, well, using our fact that I can rewrite u as a raised to the log based a of u. Right? This is our key identity, that any number u is equal to a raised to the log base a of u, because these are inverses of each other. But now this is an exponent inside there. So this is equal to, if you will, the natural log of a times log based a of u. If you're scratching your head a little bit, what I do there, I used my power rule for logarithms that say, okay, if I've got an exponent or a power here, it can come down and become my coefficient. Now, granted, when I wrote it, I didn't put it in the front, but multiplication is commutative. So to go from that first step to the other is just using our exponent rule. All right, so the natural log of u is equal to log base a times, or natural log of a times log base a of u. Solving for this, I get that log base a of u is the same as 1 over the natural log of a times the natural log of u. And this is exactly how we can go back and forth between different bases. For instance, if you wanted to calculate log base 7 of some number, your calculator doesn't have log base 7. But your calculator does have the natural log. So if I wanted to know what is log based, so put this over the side, if I want to know log base 7 of, say, 12, I could put in my calculator and say, oh, well, that's just natural log of 12 divided by natural log of 7. Right? And this is why calculators don't have every single base on them, because you don't need it. All you need is the natural log, though a lot of calculators have base 10. All right, back to the problem. We're looking here. We've got log base a of u is equal to 1 over natural log of a times ln of u. So if I want to know the derivative of this, and remember, this is a constant. Right here is some number, because a is our base. It's a number. And so the natural log of a is a real number, and this whole thing is a real number. So that's just a constant. So now, if I want to take the derivative of this, then it's related to the derivative of ln. Formally, the differential of log base a of u is equal to the differential of 1 over natural log of a times natural log of u, which is equal to 1 over natural log of a, because that comes out, times the differential of ln of u. I guess I should keep my parentheses. And the derivative of natural log of u we just calculated, and this is simply 1 over the natural log of a times u, du. So the derivative of log base a of u du is 1 over natural log of a times u. Fantastic. And now that we have logarithms, we can compute the derivative of exponents. So this will wrap up this demonstration. So if I want to know, if I say, okay, y is equal to a to the x, I want to know its derivative. Well, using inverses, we know that x is equal to log based a of y. And recall the derivative inverses, that the derivative with respect to x of y is equal to the reciprocal of the derivative of x with respect to y. And we've just computed that. So this is equal to 1 over the natural log of a times, so in here we've got y, all raised to the minus 1, which is just natural log of a times y. Now our derivative, we want to know dy dx, and we've got a y in here. We should have our dependent value should be x, but we know what x is defined, or what y is defined as. It's defined up here as being a to the x. So then the derivative of y with respect to x is simply equal to natural log of a times a to the x. So just writing out differential form, d a to the x is equal to natural log, or it should be, well, I'll just call it that. dA dx is a natural log of a times a to the x dx. And the most famous base, e, we can compute it. dE to the x is equal to the natural log of e to the x dx. But the natural log of e is 1, and so it's simply e to the x dx. All right. That establishes our differential rules for logarithms and exponentials. In the next video, we'll run through a number of exercises in which we compute derivatives of logarithms, exponentials, and trigonometric functions.